Great. Welcome back, everybody. So Matt will take us on the home stretch. Thanks.
Yes, the man with the envious job of being between you and lunch, having you been so patient so far. We're going to do a couple of things in the home stretch, time permitting. We want to focus this now a bit more on sort of one of the most recurrent themes that we'll see in the talks from now on about sort of data-driven weather forecasting, framing a bit what it is, connecting some of the architecture choices that we talked about, trying to touch on a bit why it works, and sort of pointing to some of the open questions, some of the areas of exploration that's going to be happening over the next few days. And then also to make up for the fact that this isn't really a full tutorial, giving you some QR codes and pointers to how you can go and do some interactive stuff yourself. I just wanted to start with this sort of step back to 2020, where with some colleagues when I was at Oxford, we organised sort of events much similar to this on what's happening in weather and climate for machine learning. Some of you may have been in that audience and this audience, although I'm not sure too many. And we tried to write a perspective piece about what's happening in the space. And we had this, not very good, not very creative, sort of soft, medium, and hard sort of weather forecast, machine learning for weather forecasting. So soft is machine learning as an accelerator, trying to make better use of GPUs. Medium is embedding sort of machine learning sort of in physics-based schemes, but trying to learn something that would improve your system, and for example, learning a new closure scheme. So still sort of bringing some novelty, the idea that you could improve the model. And then hard being learning forecasting systems. And this is why you shouldn't listen to me, is because we wrote in this, there's a couple of other sort of co-conspirators in this, and it is currently difficult to envisage hard AI, so learning data-driven weather forecasting systems, outperforming and hence potentially replacing numerical models on medium-range timescales. So now I have the pleasure to eat my own words, because I'm trying to implement a DCMWF with colleagues like Mihai and others, building data-driven weather forecasting to do this. So when someone says it can't be done with machine learning, I no longer say that, because it's not meaning machine learning can do everything, but it's easier to say it won't, and that be wrong. So what's happened since then? So I've got to apologize to lots of people in this room, which is I used to try and keep up to date this sort of timeline of what was happening in the space, all the different papers, and then I just gave up because it was just too busy. So this is the first few papers that really talked about sort of what you could be doing. They show what was possible. We've got people from NVIDIA in the room who helped start that. We have colleagues of Ryan Keisler, who's now back in the field, who started this back in 2022. The concept had been pitched. I'll tell you what the concept is in a second. Building a weather forecasting model from historical reanalyses alone, and then just grew and grew from there onwards. We see people pushing the boundaries of resolution. We see people pushing the boundaries of skill, of probabilistic forecasts, and etc. And eventually it got to the point, it didn't even take that long, I would maybe argue, that ourselves at ECMWF and other operational centers said, this is going to be a part of the forecasting system of the future. We may not know, and this is why it's framed as a question mark, I can't remember what the title is, is AI going to transform weather and climate? I think it will. We don't know where the settle point will be in terms of the balance of the models. We all will have our different opinions of how much machine learning is going to dominate weather forecasting, how much it's going to be an important role in climate, but it's definitely going to be there. So what is it? What am I talking about when I'm talking about data-driven weather forecasting? Well, I talk about sort of the first step of this revolution is about building something that's just replacing the forecasting part of the task. So someone comes and gives you an analysis, a state of the atmosphere right now, and then conventionally, we used to use an NWP model. We still do use an NWP model indeed to move that further into the future to make a forecast. But now we see the ability to learn from years of historical analyses, reanalysis, to build an incredibly accurate, and in some cases more accurate, model of this that's able to go from the same analysis, but then be independent of physics-based models to make a prediction. I'm going to be talking about the sort of one flavor of these data-driven models, but I'm looking forward to Stefan Hoyer's talk, where he's going to be talking about neural GCM, which is one slightly different sort of alternate on data-driven modeling. So what are you trying to do then? You're trying to learn a model from, say, 40 years of Era 5, but other data sets are increasingly being tested. And typically these models are making huge steps in the atmosphere compared to a physics model. So the IFS, ECMWF physics-based model makes, I think, a sort of a 9-minute time step to move forward in time. These models are able to stably and accurately predict forward with 6, 12, 24 hours. So there's already a big difference there in terms of how this model is moving forward very quickly in time. You're making a model. If we talk about what are your inputs and outputs of machine learning, someone's hungry, that shares many of the same inputs and outputs. We want something that predicts practically all the things that it needs to make a prediction so that we can auto-regressively apply it to itself and step forward multiple times. So we don't try and make a forecasting system jumping independently for these different time steps, but we say, learn something that can make a 6-hour step and then apply it to itself several times to make a forecasting model. So, and why this is exciting? Well, this is exciting for lots of reasons. I decided to resist any urge to put any comparisons of scores or other things. But lots of people will talk about that over the days to come. But we see less discussion maybe about energy. So these sort of nondescript units are how we measure computer use on our HPC at ECMWF. We measured that it took sort of 15 billion sort of units to build Era 5. It takes about sort of 180,000 units in our supercomputer to make a single forecast. And depending on the model, it takes about 0.3 units on this system to make a data-driven forecast. So once the sunk costs of building this giant training data set are there, and Era 6 is only going to be even bigger of that, the opportunities for having it be much faster, you to run more ensemble members, or just empower more people to run forecasting systems themselves, for example, perhaps in sub-Saharan Africa, are very sort of potent. So what is the training objective? So we are tasked with taking an input state from the Earth system. So this is most of the sort of fields that we would want to have the model predict and also think are important to make predictions. So this is variables at around 10 pressure levels in the atmosphere, surface fields, precipitation fields for winds, humidities, temperatures, geopotential. We're then going to task the model to reproduce that state, but further out into the future. And we're going to take Era 5, divide it up into training, validation, and test data sets so that we can understand the impact, and just run through this training algorithm. So checking the accuracy, making the gradient descent, and then building iteratively a better and better system. To give you a context, sort of for the AIFS, this takes around 50 passes through the data set to get to the state-of-the-art accuracy. So you think about going through from sort of 1979 to present day, about 50 times to get there. So what are the key design choices in this? So this is where I want to connect back to what Mihai talked about earlier. So the first is sort of how spatial information is incorporated into data-driven forecasting. So I'm going to talk about 3 different architectures that you'll then see sort of brought out in some of the talks over the next few days. So the first are graph neural networks, which Mihai has just done a wonderful job of explaining to us. My favorite thing about graph neural networks for weather forecasting is the very natural encoding of the sphere. So we're going to draw contrast to that with transformers a little bit, particularly vision transformers. And we know, because they've been used in lots of other areas of physics, that message passing graph neural networks are so-called very expressive. You can build in very high complexity into them. And it's been shown to work in lots of other physics problems. Because they end up sharing so much information, you build information and put quite a lot of priors on with these graph neural networks, they end up being relatively light in parameters. So what does this mean? Well, I think you can build something that is using sort of 10 to 100 million parameters, so still a large number, but that's typically maybe an order of magnitude smaller than those would be required for transformers. However, their disadvantages are, as Mihai has talked about before, they're not the most computationally efficient. So they have lots of sparse algebra to go about doing, and GPUs are just not, they're good at it, but they're not optimal at doing it. So there are lots of examples of this, work from Lion Keisler, the GraphCast, GenCast, and the AIFS, but many more beside that. So then transformers. So Mihai's talked a bit about how transformers work. And what we saw, particularly with the first set of generation of these models, is people building on the vision transformer community. So this is thinking about the Earth as an image. And here, the way you use transformers is to use this so-called shifted window vision transformer. So here, Mihai talked to us about sort of how attention allows you to pay sort of to incorporate information, propagate information between different patches. And so what you would do within a single layer is have a window of attention like this to mean that the computational costs don't grow of having every patch over the globe talk to every other patch. But if you have lots of layers that put that window in exactly the same place, you'll only have information propagate over Europe, and you won't have a good, effective way to have information propagate from Europe to Asia to America. And so what you do is you make a series of layers that all use these windowed attention, but they shift the center and the boundary of the window. So this means that this point in this nice sort of castle is at the edge of this window and near the middle of this window in subsequent layers. And this allows information to propagate over these vision transformer windows more quickly across the globe. It allows information to move more quickly. The disadvantage of this is sort of the larger number of parameters. The counterintuitive thing is they are typically way more computationally efficient, and that speaks in part to do with the fact that we're really building on a much bigger sort of community when we do this. We are able to build on the technology of the sort of natural language processing, the sort of computer vision community that are all making these things incredibly efficient. They're all working on the underlying algorithms and making them work very, very well. So we can have a larger number of parameters, but we can still train more efficient. But what you might see with a certain sort of smaller data set problems, let's say you only want to build an atmospheric chemistry model and you only have a smaller number of years, this larger number of parameters might make it harder for you to train to convergence with this larger number of parameters. There's also, if you use sort of shifted window models out of the box, you could find a sort of suboptimal representation of the poles as you have these sort of cylindrical representation converge to try and make points meet near the poles. And I think in some places, we do see that there can be artifacts that emerge when you run models like this out for a long time. So the third architecture we want to talk about is the sort of Fourier neural operators. So I think you'll hear about this in at least 2 talks. Boris is going to give an update from NVIDIA, and then the ACE group is going to talk about this. So here, if we think about how information is incorporated, this takes a slightly different approach. So here you transform into a set of coefficients of Fourier Legendre wave numbers, and then say you are doing neural networks both on that wave number space and then on the grid point space. So this allows the learning of local operations and also global operations. And it has a wonderfully elegant sort of representation of the poles, because the sort of spherical neural, the spherical Fourier operators, sort of they are a very clean sort of representation of the sphere. And we're seeing particularly very active use of these in seasonal and climate modeling, as Ollie will talk about in a few days. So we talked about space. What about time? So I talked about the fact that we are training these models to make a 6-hour prediction. What's typically done, particularly in the weather forecasting domain, is to not just train them to do one step, but we do to introduce some jargon, some rollout fine-tuning. So fine-tuning is the idea that you would take a model designed for one task and then task it to do a slightly different task. You might adjust the learning rate to make it able to learn this slightly different loss landscape. So what does rollout fine-tuning mean? It means you take a model that's been tasked to do a one-step prediction for 6 hours, and then you apply that model to itself while keeping monitoring this gradient information. So you apply the model multiple times to itself on its own output, and then backpropagate not only through one copy of the model, but through all the copies of the model to understand how the sensitivity of the design choices your model made here impact your model, say, 72 hours in advance. And then you weight your loss. Your loss is then comprised of the loss at each of these forecast steps and allows you to directly target making a short to medium range weather forecast all in one go. So why does data-driven weather forecasting work? I think everyone has their own sort of version of this story, but I wanted to give you sort of my take a bit. So ERA 5, we're using what's called sort of 4D variational data assimilation. So what does this mean? Well, we start with a so-called sort of background trajectory, which is our original thought of what was happening over 12 hours. So that's a physical model forecast. And then we, in a process of minimization itself, of minimization of the atmospheric state, we try and find a better state through, again, gradient descent. This is with a physics model to better match a set of observations. And this window is 12 hours long. That's a design choice. And the thing worth noting is that all of the leading data-driven weather forecasting models, I think this is true, someone can shout us if I've missed one, are minimizing mean squared error over greater than or equal to 12 hours at some point in their training. And what does this mean? Well, this means that they're stepping across multiple windows. Because what happens if you sort of, with the physics model, run that out with the end point of your analysis, the output of minimizing these observations into the next 12 hours, well, you get to, in fact, that is the definition of a background. And that doesn't fit particularly well from these observations. But we're not training from that. We're training to step from data assimilation window to data assimilation window. And so we get the best of both worlds. We get the observations that are there, and we get the model filling in the gaps. And we find this trajectory, this combination, or we aim to have this trajectory of green going into black, that a physics model is not capable of doing it. We're trying to make physics models better. We're trying to make them better fit this, but currently we don't know how to do this. Now, obviously, we can't learn a perfect relationship, and it still wasn't obvious, hence my quote from myself at the beginning, that there was enough data to do this. But this is a sort of after-the-fact explanation of why it's possible to use a physics-based model, build a model that's better than that physics-based model. So we talked about rollout, sort of optimizing over long time steps. I've just talked about why it's a good thing, and I want to talk about why it's a bad thing, just to keep you all on your toes, and the impact of optimizing over longer time windows. So I want to take you back to this earlier thing. We're training these models typically at the moment to minimize a mean squared error. And we talked about right in sort of the first section, when you minimize a mean squared error in a sort of uncertain problem, you're going to get ensemble mean sort of like behavior. You're going to damp out the things that are not predictable. And what we've seen with all of these great models that have been made open source and available is a real spectrum of the more you train for longer lead times, the more you get smoothing. And the more you get sort of changes to your behavior, the more you get behavior like an ensemble mean prediction, not a trajectory of information. And this is just two different ways of looking at this. So this is showing how energy is located in the atmosphere for our ensemble mean. So that is an ensemble of the mean of an ensemble of forecasts of physics-based models. And what you can see is over different lead times, as you move from 1 day to 4 days to 6 days to 10 days, your energy throughout the atmosphere gets less because you don't have predictability on those scales. So if we take a model like Pangu, so Pangu is interesting because it makes a one-step prediction but doesn't use rollout, so it's only optimizing for 1 day, we see it loses information on some small scales but doesn't really lose information on the larger scales. If we take another example like Fushi, this directly optimizes all the way out to 15 days, and you can see it is losing energy through the forecast at all timescales. These are all valid design choices, but you get what you're paying for. So if you are optimizing over long timescales for a deterministic problem, you're going to get something that looks more like an ensemble mean product. And I would say, in my view, there are fewer use cases where that on its own is useful information. So weather is an inherently chaotic problem, and a deterministic framing is holding us back. Hopefully that's obvious. So very quickly, how do models deal with uncertainties? How do we make sort of probabilistic predictions with first physics models? Well, we have to capture a representation of both initial condition uncertainty and a representation of the uncertainty of our model. So initial condition uncertainty, at the moment, if we're thinking about this paradigm of building on physics-based models, building on analysis, we do this already for physics-based modeling, so we can keep this. So what we really need to do is learn how to represent model uncertainty. And that's something that you'll see as another theme through the days to come, is this second phase of learning data-driven weather forecasting models, going from deterministic to probabilistic forecasting. So there's a couple of ways to do this, and we might see more as time goes on. I'm just going to highlight one approach. You'll hear about diffusion modeling, diffusion forecasting. This is something I don't have time to go into enough detail. Suffice to say that it's asking you to learn how to shape noise into a prediction of a future state. And because you're learning how to shape noise, this means you can give another sample of noise with the same condition of where you are now and give a different prediction out. So it allows you to learn sort of without making a parametric assumption about the uncertainty of your future state. Another way, which we've been working on, at ECMWF, is directly optimizing probabilistic skill scores. So you swap out the mean squared error for, so the CRPS is a good skill score for measuring probabilistic behavior. You also see this, I think Stefan will talk about it. He did some really nice work and colleagues with this for neural GCM, where you directly learn to shape noise so you just replace one score with another, and you have to propagate an ensemble forward to get that. Foundation models, we're going to hear a bit about those in the next few days. I guess the key thing to note about them is quite a few of them are really using this self-supervised learning approach. So the way they train is you can see schematics from both these papers, from AtmoRep, from Christian Lessig, and from Prithi, which now has a follow-up paper, where what they're doing is taking their space-time images of the Earth and masking out some of them, and then aiming to fill in the gaps. And the argument that you're making here is when you learn to fill in the gaps in any point in space and time over some window, you will learn forecasting, you will learn perhaps downscaling, you will learn time interpolation, all as a single model. A slight alternate sort of take on this sort of foundation models, so foundation models being something that you can then use for lots of different purposes, is the Aurora model. So Aurora was always training as a forecasting task, but the types of data it aimed to train on varied a lot. So they trained on ERA5, as most people for their data-driven weather forecasting models did, but they also trained on CMIC6, they also trained on GFS, and they also trained on atmospheric composition data and wave data. And so the idea is that they're learning a model that can operate in lots of different forecasting contexts. So I just wanted, because this Exclaim Symposium has a history of working a lot on sort of this frontier of HPC, and I just wanted to show that there's some really interesting challenges and opportunities in this space. Sort of parallelism is increasingly an important feature of how we build these data-driven models. So batch parallelism, which someone can ask me a question on this, offers sort of effective and easy scaling up to a point. But we know that weather forecasting and climate modeling are global problems. And so so what that means is we need information to move on a sort of quarter-degree grid to communicate one point to any other point on this. So we need sort of, at some level, connectedness between all of our points. So we can't just sort of take a sample and train only on that sample over Europe. So this has a lot of grid points. And then it also has a lot of variables. So you're interested in your state space that's coming in and out has hundreds of millions of data points. This can get to a non-trivial perspective to fill them in to a single GPU memory, and means that we're now having to sort of build some of the same parallel implementations that we see in weather and climate modeling for our sort of our data-driven weather forecasting. So this is about domain decomposition, halo exchanges, all these things that you might know from if you've worked on sort of HPC for weather and climate. Propagating information between GPUs is increasingly an active thing to work on to be able to move to higher and higher resolution. So a few unanswered questions so that we can have some. What about data assimilation? I didn't have time for it. There's loads of really interesting stuff going on in this space. Mihai's going to talk about it, and it's a really interesting next frontier for how we can build these models to make them even better. What about climate? We're going to see at least one, probably more talks on what's happening in the climate space. What's really interesting here is some of the design choices actually look different from weather and climate at the moment. So this whole idea of rollout fine-tuning, I think Ollie's going to talk about how that doesn't actually necessarily make the best climate model the most stable climate model. And finally, You can do all of this yourself. It's relatively easy to go about building these things yourself. And at ECMWF, in collaboration with lots of others, we're really trying to make this as easy as possible. So I'm inspired by how easy some of the first papers made it. So AIFS, our machine learning model, is sort of open, and there's a sort of a Jupyter Notebook showing how you can make predictions very easily. I should say it's much easier if you've got a GPU. We need to work on that. Where there's just sort of in just a few steps of downloading the data, downloading the model, you can be making a prediction that is equivalent to our operational weather forecast. So you can rerun our operational weather forecast on your own GPU. You can also train these models yourself. So underlying sort of the AIFS, which is ECMWF's machine learning model, is Anemoy, which we've been collaborating on now with an increasing number of partners across Europe, including our partial host, Meteo Suisse. And this is aiming to be a toolbox to help you build sort of data-driven weather forecasting models. So we've got some tutorials, some guides on how to do this. We're trying to make them better. But if you want to learn more, you can go and look at these things yourself and come and ask us questions. So with that, you're not allowed to go away because you might have a question for me, and then Ollie has to give you the guide of what's happening over the afternoon ahead. Thank you very much.
So we have a bit of time for questions. Okay with the catch?
So you mentioned the computation constraint for high resolution. So for global model with high resolution, it's that's a bottleneck for the high resolution. But what about a regional model?
Well, so there's a lovely poster outside from colleagues at Met Norway, where they've been doing a combination of global and regional sort of but even if you just solve that as a regional problem, when you have kilometer scale data over a large enough region, so there are 1 million grid points covering the sort of Nordic domain. There are 500,000 grid points to cover the whole domain at 1/4 degree. So it's a big data problem where we're headed either in local or global. We're all going to face this because we have very nice high resolution data sets that we can train on.
Round. So I'm interested in how you apply a constraint to these ML models. For example, in climate, it would be really nice if the atmosphere didn't lose mass. How do you apply conservation of mass to one of these models? And which models do apply constraints?
Where's Ollie? You're here. Are you going to talk about this? Okay. This is why the slides are being made live, so that we can see what questions are. I mean, I guess we've done this a little bit with the AIFS on some of the most basics of what's happening. So like enforcing positive definiteness on precipitation, which you can do with custom like activation functions are the last thing. So typically in machine learning, the last layer doesn't have an activation function because that might constrain what the predictions you would want to be. And you want to have you might want values to take any value between -infinity and +infinity. But you can put constraints on with activation functions to do some of that. If you want to write down sort of global constraints like mass balance, there are also ways to basically take away a degree of freedom somewhere to say, well, that last piece of information is filled by constraining this. So, and Ollie will now have a slide on that to go into more detail. Good question.
Thank you for the nice presentation. Before going to ask my question, I'll just sneak in an invitation to my poster regarding the concept of physics constraints. I have been working on it and I have a poster on it, so we can discuss about it. Yeah, so regarding the questions, I have many, but I'll focus on 2. What about the evaluation metrics that we should use for evaluating these machine learning models, basically? Because we are dealing with spatial domains and temporal domains, and how do you define the mean? Because the models are normally predicting the means very well, but you have local variations, local gradients that are not very well captured, especially the magnitudes. So what sort of evaluation metrics we should recommend for evaluating these models first? Second question regarding the soft part of your ML paradigm. Has the community certainly given up on that, or is it still worth looking into, specifically considering the difference between the online versus offline training of these different components. Yeah, thanks.
I'm going to answer the second one first. I think the community is certainly moving away from it. It's not an empty space, but I think one of the realities came out was it's actually hard to like accelerate that way. So I worked with Peter down at the front on radiation emulation, and Peter had two hats on because he helped me build emulators of radiation. He also made the radiation code faster as is, and it turned out that you would be better spending your time in optimizing the existing physics code rather than sort of building an emulator in that context. I think the challenge is that the parameterization schemes aren't necessarily that complex, and so there's not a lot of complexity to learn. So like, and I'm not going to say the whole field is dead, but I think there's way less energy than was, and it was a bit short-sighted, myself included, that thought this was going to really give us a big order of magnitude. I think the other challenge is, if you look at sort of a weather and climate model where the computation is spent, it's very diverse. So it's not, even if you make one component twice as quick, that's very negligible on the overall footprint. So it's there, it's less. I'd say there's still lots going on in the sort of the medium AI of making things better. We've got some work going on at that ECMWF. The first question was around metrics. It's a really good one without a great answer, except to say, my impression is we already have lots of the metrics in the community already. It might be about sort of re-raising the awareness of some of them. So things like spectra, there are groups that already look at this on a regular basis, but it's maybe not commonplace for everyone to do. But we should be challenging ourselves to plot the spectra and understand what's happening at different length scales. Sort of similar, we have metrics for like spatial coherence of precipitation, for example, like area aggregation precipitation is one way to do that. There are lots of others. And so there's lots there. I don't know we need to invent new ones, but we need to be diverse in looking at these forecasts in lots of different ways.
All right, I think we've reached half past. I'm sure your tummies are grumbling already. So first of all, I'd like to thank all of you for coming and engaging so actively, but I'd also like to make sure to thank Matt and Micha, maybe you can get up, for preparing this tutorial. So thanks a lot. Can I grab that?
Yeah. You can get back down now.
So now's the lunch break. We'll start again at 2 o'clock in this same room. So make sure to be back for the formal opening of the Exclaim Symposium by Nikki. There are a couple of lunch venues around ETH, which are convenient. And so if you want to snap this QR code, you'll probably find a way to a convenient one. And thanks for that, and see you in the afternoon.